Welcome back. In this lecture, we are going to look at the matrix representation of quantum gates. Now, this matrix representation is very important because we know how to deal with matrices. You all are familiar how matrices look. They look something like this. And we know how we can operate on these matrices. We know how the linear algebra works. So therefore, we represent gates as matrices. And this is quite consistent. This is not just in quantum information science, but in overall quantum mechanics, we represent any given operator as a matrix so that we can play around with it or calculate whatever we want. Therefore, linear algebra is in general very important for quantum mechanics. Okay, so let's start. So you would remember what a quantum gate is. So we simply take any input A, we apply some gate on it, let's say U, and we obtain an output, let's say A dash. So that is very simply a quantum gate. Earlier we looked how we represented quantum states in Dirac notation. So earlier we looked how we represented our quantum gates on the block sphere, something like this, and then we see how the gates work, rotated, on all that. Now we will look it in the terms explicitly of matrices. Remember that to describe this gate, again we are dealing with the Z basis everywhere. The crucial information is what this gate does to our 0 state and to the 1 state, because if we have this information, we can take any arbitrary quantum state psi, let's say alpha 0 plus beta 1 in the Z basis, and map out what the gate will does, because this quantum state is a superposition of 0 and 1. So here's what we do. We look at our quantum gate and see what it does to 0 and 1. So for example, here it adds coefficients A and B respectively to 0 and 1. If we apply it on the 1 state, it adds coefficient C and D. And we can represent this as column vectors. I hope you're familiar with this notation from the Dirac notation. And so once we have this information, we can easily plot a U gate as a matrix. Here, so this is our U gate. Color. This is our gate U. And so let's see if we have the gate, what can we do with the gate? So we can simply obtain what the gate does to a given vector. So let's say, for example, we want to see what the gate does to our state 0. We have the matrix notation of a gate, and we simply do matrix multiplication. 0 is represented as column vector like this. This is 0, and 1 as a column vector as this. This is simple Dirac notation. And so when we multiply these matrices, we obtain AB, which you see is similar to this thing. Exactly, we repeat the same procedure with 1, and we obtain the same thing here. So if we have our quantum gate in this matrix multiplication, we can simply multiply our vector or our quantum state and obtain the new or the transformed quantum state, let's say something x and y. Just run it. Here's a better description of the same thing. We start with our quantum state psi, which is represented as alpha 0 plus beta 1, and here's a column vector. We want to operate on this state with our gate U, and our gate U here is the same thing, and any arbitrary gate with matrix elements as A, B, C, and D, and we operate it. So we know how this simple, this is just distribution here, because we are dealing with linear algebra, so all the rules apply. You can follow through this notation very easily, and we obtain this as our final state. And you can see the same thing when we do the matrix multiplication, right? We have this gate U, we have the state alpha beta, and we obtain a final state, let's say phi. Let's say phi. So it was so much simpler in matrix multiplication. That's why we want to use matrices. Another important thing is that the matrix representation automatically preserves or must preserve the normalization. That is, the total probability should still be 1, this probability of observing a state. So this should still remain 1, which you can easily follow through this notation here. So quantum gates are matrices that keeps the total probability equal to 1. Let's look at an example here, just to make things more clear. So to represent a quantum gate, we need the basic information. What does it do to my basis states, 0 and 1? So we see, what does it do to 0? It transforms the 0 into this and 1 into this. Simply, we will take the coefficients. So this is a coefficient A, it's a coefficient B, and put it in a column vector. It's a coefficient C, it's coefficient D here, and put it again in a column vector. And when we combine these two column vectors, we get our matrix U. It is represented by matrix U. Right. And to apply this matrix on any arbitrary psi, where psi is again alpha 0 plus beta 1, we would simply write this matrix U and multiply it with a column vector to obtain something new. Okay. Let's go on to the next topic. Now we will see the common 1-qubit gates that we discussed in the last lecture as matrices. So here are the representations. Again, just to remind, to represent any gate as a matrix, we need the basic information. That is, how does the gate transform the basis states 0 and 1? So for example, the identity gate, it does nothing, just 0 to 0, 1 to 1. And so we will get our A, B, C, D. Let me put it in a better way. Our A is just 1 here, and B is 0, C is 0 here, and D is 1 for the identity gate. And this notation is being followed from here, this part. Okay. So when we combine all these, we get this matrix I. Similarly, for the NOT gate or the poly X gate, you can follow. We'll get our A is equals to 0, B equals to 1, C equals to 1, D equals to 0 from this transformation. So I can write this as A0 plus B1 plus C1, let's say D1 plus C0. So here's how we get that. You can follow through as an exercise to obtain all these gates as matrices. So you see, this 1 by root 2 automatically comes from here, the normalization. So the matrix representation automatically preserves this thing, right? So let's look at the identity gate for a second. Let's try to operate it on any arbitrary state psi, which we can represent like this. And so this is our identity gate I here. We operate it on our state psi, and we can easily follow through this, and we get the state alpha beta. Let's try to apply this on an example, which is this thing. This is also a plus gate. So let's first write what the plus gate is. We know that our plus gate is represented like this in the Z basis. Okay, and we'll try to apply the identity gate. So this as a matrix can be represented like this, right? I hope you're familiar with this. Now let's try to apply the identity gate on this state plus. We take our identity gate 1 0 0 1 and 1 1, and we apply this thing. Because it's a constant, we can simply bring it out here, and when we apply it, we get 1 by root 2 that follows from here, and we get 1 1. So we indeed see that this thing remains exactly the same. So we get our plus state back as it is. Let's look at another thing. Let's look at the poly X gate from scratch. So poly X gate is basically the NOT gate. So first let's obtain the matrix representation, and you can easily follow. Here our A is equals to 0, B equals to 1, C is equals to 1, D is equals to 0. So our matrix representation will be A, C, B, D, which is nothing but 0 1 1 0. So this is our gate X, and let's try to just apply it on our state, let's say 0, just for simplicity. Okay, and you can of course map it using this, but we'll try to apply the matrix representation. So this can be represented as a column vector like this, and let's try to apply the X gate on 0. We have 0 1 1 0 times 1 0, and when we apply it, we simply get 0 1, and this is the 1. And so here we can easily see how this thing, when we rotate it, which is the NOT gate or the poly X gate in this case, we get this vector. Okay, so let's move on. Now we will try to apply these gates or these quantum gates in series. What does that mean? We discussed this last time as well. We take in input A, we apply multiple gates. Let's name these gates 1 2 3, and we finally get an output, let's say B. Now of course the order we apply is simple. We first apply the first gate, then the second gate, third gate. This is all you need to know about applying multiple quantum gates. And so here as an example we see this. So first what we will do, apply the Hadamard gate, next the T gate, the S gate, and the H gate. Now remember when we did it earlier, this was so much more complicated because we were doing it in Dirac notation. You can go back to lecture number 3 and look this up, and it was so much more complicated. But now we have the matrix form of our gates, so we can represent this whole thing easily at once using the matrix form. See, so this is our state. This is our state 0. This is our Hadamard gate. This is our T gate. This is S gate, and this is again the Hadamard gate. And now we just simply multiply matrices, which can be done using a computer. You might be familiar with MATLAB. This thing becomes so much more simpler, and we obtain the result easily. So you see again in use why we should use the matrix form of the quantum gates. Next, we are going to look at unitarity. So what does, just to recall what we did in the previous lecture, in the previous slides, we took a quantum gate U, and we represented how we saw how it acted on the basis states 0 and 1, and we formed a matrix representation. We have operated the gate. This stems from the Dirac notation, which we saw earlier in this slide. Here, how the gate U acts on psi, and effectively we could bring this inside. So that's what we have done here. We just brought the U inside the state. Now let's try to take the conjugate transpose. What is a conjugate transpose? Let's break it down. conjugate and transpose. So a transpose of a matrix is simply, if the matrix is A, B, C, D, we take the transpose, we get A, C, B, D. So we simply switch the rows and the columns. That's the transpose. And what's the conjugate? If there is any complex numbers present, let's for example take x plus iota y, and a different example, say anything else, let's say p minus iota q. When we take the conjugate of this matrix, what we would get is, it's just the conjugate, we are not transposing it. What we would get is x minus iota y. So the complex part flips, and p plus iota q. This is the conjugate. And for the same thing, if we want to take the transpose as well, so conjugate transpose, so we'll take the transpose of this matrix here. This is a column vector, so we'll get a row vector here, x minus iota y, p plus iota q. So this is conjugate and transpose, and when we combine those two things, we get conjugate transpose, which is also represented by, let's say this is matrix like this, like the plus symbol or the Christ symbol. Okay, so we take the conjugate transpose, the star represent the conjugate. So it's really simple. We assume that these coefficients a, b, c, d are complex, and even these coefficients alpha and beta are complex. So we assume everything is complex, and therefore we take the conjugate of everything. And this is pretty trivial to follow, and we get this. Now we can see this A, B, C, D, and when we transpose this, we get this matrix. You remember this symbol, so we just use this symbol to denote that this is a conjugate transpose, and we obtain this. So what does this mean? This means that u psi is equals to psi, and this is conjugate transpose. This is similar to the place where we started. So here we brought in this u into our state, and here we brought out this u. So this is what unitarity means, and this is what it represents. You can further convince yourself by using this matrix identity, and is how we transform from a column vector. Let's say if our state psi is equals to alpha 0 plus beta 1, if we take the conjugate transpose, this is our ket vector. If we take the bra vector of this will simply be the conjugate transpose of this, which would be this. So let me just write the matrix part effectively. This would be alpha star and beta star, right? Or the conjugates here, because the transpose is simply from the column vector to the row vector. This is column vector, this is row vector. This is simply the transpose, and to take the conjugate, we represent it by star. Okay, and this is a simple line of proof from which we essentially get the same thing. So to summarize, this is again the same thing I wrote here, but effectively this is the main thing that you need to remember. Did we forget about anything? Normalization. We know that the quantum gates are themselves normalized, and this can be simply proved by the part if we take the inner product, because that is what we do to normalize any given quantum state psi. We take the inner product psi. If I try to open it, this is over all space, psi star, psi and d, whatever, let's say, because it's over all space, or if you want to take in one dimensional, and this probability should be equals to 1, and this is what we obtain. Or if we want to write the matrix form, the 1 is represented as the identity matrix. This is what we expect. So a matrix that satisfies this property, U transport conjugate times the matrix U itself and the reverse of it, which is called unitary matrix. Thus, all quantum gates do satisfy. It turns out that all quantum gates do satisfy these properties, and they are therefore unitary matrices. Let's consider an example. We take a gate U. So let's check if this is a valid quantum gate or not. So we have this quantum gate U. We first try to calculate what would be the transport conjugate of this thing. So this is constant, so it simply remains like this. But the transport for the transport conjugate, let's first try to conjugate this. So 1 is real, it will remain like this. Iota is complex, it will have minus iota. Minus iota is complex, it will become plus iota 1, and then we can take the transpose of it, which would simply give us this. So we essentially got our matrix back. See, this is the U matrix again. This is the U matrix. So this, in this particular example, it became U square. This is not necessarily true, but this is just a side note. When we multiply these matrices, we obtain this, and we obtain this state. And you can clearly see this is not the identity matrix. The identity matrix looks like this. Therefore, this is not a valid quantum gate, because it must be unitary, as we saw here in the statement. Okay, let's go on to a next concept of reversibility. We looked at this concept in the previous lectures as well, where we try to say which gates are reversible and which are irreversible, and we mentioned that only reversible gates can be quantum gates. So here we have the same definition but in the matrix form. So a matrix M is reversible or invertible. I hope this you remember this word invertible from your linear algebra, and the inverse of a matrix M is represented as M inverse, and there are ways to calculate this which we will not go into detail right now. But a matrix M is reversible if there exists a matrix denoted by M inverse, same thing, such that M times M inverse, or the reverse order, is equals to the identity matrix. And since we are dealing with our quantum gates, we know that our quantum gate must also be unitary in this condition. Therefore, this should also be true. So when we try to take both of these conditions into account, we obtain a result, and this follows because we know that the transport conjugate of a matrix U is also the inverse of the matrix. So the inverse of U is simply U transport conjugate, that is this thing is U inverse is U transport conjugate. So a quantum gate is always reversible, which follows, which we already have discussed, and it must be reversible, and its inverse is its conjugate transpose. So we get this thing, quantum gate U is always reversible and its inverse is the transport conjugate of the gate. We can represent this as like this, because we know that U transport conjugate times U is equals to I, and when we try to operate, we get our state back, psi. So this is the end of our lecture of the matrix representation of gates, and here are some exercises for you to try. So this exercise, you consider this operator U and try to answer these questions, and you can do the other exercises. If you have any doubts, you can contact me in my office hours. Thank you.